let's go. So much to talk about. My God. My God. So, you know, I didn't read the syllabus. I don't know if you've noticed that. And I tried to get you all in here about half an hour ago. You know, actually, that's kind of a perennial problem of mine. I was not really, my high school counselor said I wasn't college material. And, oh, they were right, for sure. And because, you know, I could tell you, I could give you all the excuses why I was a poor student, but mostly I was just a stoner rock and roller trying to get by. And so I didn't go to college until I was 30, because I had a career in the music industry because of that. And, but now I have a 4.0 and 3 degrees, not because I'm smart, but because I started school when I was 30. So I kind of knew how, you know, how to do it. And I just want to say, you know, we got the A's right up here. Look at them, right up here. Yeah. All right here. Here's the B's. And here's the rest of us. I mean, this is my home turf back here, I got to tell you that. So thank you all for coming and being interested in soil. And we're going to dig in, no pun intended, here. We're going to go in a little deep. But I just wanted to show you, here's an oxisol. An oxisol is what we see in the tropics. Remember I talked about all that's left is like rust, right? And so that's one of the ones we see in the tropics. And so I don't know if you can see this. This is the taxonomic words that describe this soil. And I want us all to read it together who can see it. We'll start with very fine. Ready? 1, 2, 3. Very fine, kaolinitic, isohyperthermic, typric, eutotorox. Yeah, you said that. You can get an A in my class. So ox means it's an oxisol. Tor means it's hot. Eutro means it's always hot. Isohyperthermic means it's hot all the time. And kaolinitic is the type of clay that it has, which we're going to be talking about here. It's a very old clay that has been weathered many times over, and it has a very, it's kind of you make pottery and stuff out of instead of growing stuff in it. And very fine means it's like, you know, fine textured. So it's like a silty clay or some sort of clay loam or something like that. You know what a loam is? A loam is approximately equal parts sand, silt, and clay-sized particles. And so a loam has approximately equal amounts of sand, silt, and clay, which means it has a wide pore size distribution because it has a wide particle size distribution. And therefore, some of the pores are large and drain, and some of the pores are fine and hold water, and that's why loam is good. So when people say, oh, it's very loamy, what they mean is it's a very nice pore size distribution. So it holds water and air. So, I don't know, I can show you a couple of, you know, I normally do talks in Oregon. I tried to find a map like this of New Mexico, because I have to tell you, the last time I was in New Mexico, I was 8 years old. So my parents drove us out to California, man, in a pickup truck from Minnesota, where I'm from. And me and my sister sat in the back of a pickup truck with just like a shell on the back in lawn chairs. And my dad was a top fuel drag racer. And so they had a bed in the back going this way up near it, and you could crawl through into the cabin back. There was no air conditioning. We thought it was great. Kids these days have no idea how much fun we had. Yeah, so my dad started out as a hot rodder in the 50s. He had a 34 Ford 5-window, really nice, chopped, did it all himself. And he ended up progressing into drag racing and eventually ended up at the top of the sport in 1971 at the Winter Nationals with front engine top fuel dragsters. And then my mom said, got to do something else, which was wise, because then he got a sailboat. Well, my mom got the sailboat. And he said, I went from the fastest form of transportation to the slowest. And so we sailed on Lake Superior for many years, and wonderful guy. And he ended up getting into British sports cars. And anyway, my dad was a motorhead. So I was not college material anyway. As it turns out, I am college material because now they're paying me to be there. So, I know these are coastal soils on the Oregon coast, and andisols and entisols and inceptisols. And this is what I want to get to. Soil, real soil, doesn't come in a bag. Soil is formed when rocks partially dissolve in water. So where there's liquid water and rocks, and then those rocks fall apart into different sized particles based on the crystalline structure of that rock into percent sand, silt, and clay. And the dark colored minerals weather out first because there's a whole reason for it, but they're the ones that dissolve easily, and those are the ones that have the important mineral nutrients for biological organisms. And once that happens, then we start to get things living and dying, living and dying, living and dying, pumping carbon and energy, carbon from the atmosphere, energy to the sun into the soil, which allows for more energy to be stored in the soil like a battery, so that the billions in a single pinch can eat that organic matter to get the carbon, to get the energy, and to get the mineral nutrients, and so that they can reproduce. And so there's more of them, and the more of them there are, the more plants can grow there. And the plants themselves, the roots, they push down in, and I don't know if you've ever seen a root before. The root starts out as a big thing, and then it bifurcates into a smaller thing, and then it gets into more smaller things, and pretty soon it's tiny little things. And all of those are pushing the soil. As the root grows, it's pushing the soil away, using the energy of the sun, right, to do that. And then it dies, like everything. And then when it dies, what happens to the root wad that's in there, that big thing? It rots away eventually because the billions in a single pinch ooze out enzymes that are catalysts that allow for the oxidation of that wood to go off as CO2, water vapor, heat. The energy goes back into other life forms, blah, 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 and all that stuff. And what's left behind is a casting of that root, because it all goes away. And what is that? It's a casting. It has a large pore, a medium pore, and a small pore, and a super tiny pore. And so those roots are creating a more wide pore size distribution. And they have been selected to do that because by doing that, they make the soil better habitat. More deeper water penetration, more air deeper down, so that more organisms, so the next generation of roots can actually follow the old casting and go deeper and make it more diverse. And the plants that did that were more successful, and the ones that didn't, and that's why soils are what they are. They're shaped by biota. The physical pore structure, those connected pores of old roots, they go in, they live, and they die, and then they go away. They go in, they live, and they die, and they go in, and they die, and live, and die, and live, and die. And then all of a sudden, there's a whole bunch of organic matter there with a wide pore size distribution. And that's what soil building is. Soil just builds on its own. It's a self-organized natural body, a four-dimensional complex habitat, a living thing. What's the answer? Add organic matter. What's the answer? And the easiest way to add organic matter is to grow it. That's what plants are doing. They're leaving a lot of organic matter underground in the form of roots. And sure, there's a bunch of stuff on the surface, and the worms and stuff will pull that down. But just consider that some species of plants and trees, you can put them in different soils, and they'll express their rooting structure differently to solve problems. Some of them can't. Some of them have the genetic memory, if you will, to be, oh, when we're in sandy soils, we should do this. And when we're in clay soils, we need to try and drain it more, or whatever. So we're expressing the phenotypic expression of those genes is different in different soils. And some soils are quite, some trees and plants are quite plastic in that regard, and some of them are very rigid. You put them in the wrong soil, and they can't adapt. They don't have the genetic memory, if you will, to do that. So just kind of put that in your pipe and smoke it. And just think about that a little bit. And what they're doing is they're injecting carbon and energy into this, and what you're seeing here is real soil. Look at this. If you look, there's this cracks right down the middle. See that tiny little gray cracks right down there, right in the middle? See that? So that was once a root. A little root went in there, and the tiniest pore you never saw because it's microscopic, that was filled with water, and that little root went in there, and then it got bigger, and then it died. And then it went back to CO2, water vapor, heat, and left a little ash behind. And the next generation did that, next generation did that. And that is the self-organizing sort of properties of soil and plants. The plants make the soil better for having more plants, which allows for more plants to be there, which adds more carbon, more energy from the sun into the system, which makes it better for growing more plants. And the more plants that are there, the better it becomes for growing plants. And you see what I'm saying? And that's what soil building is. That's what a forest is. And that's what happened where there's mollisols, because there were grasslands. And grasslands are there because of a dream of a dog. I don't know if you're ready for this. You ready for that? This is from Greg Retallack, like metallic, but Retallack. Thank you. He came up with this hypothesis that the Midwest United States, where all those mollisols are, we saw in that map there, that's because of the bison were there. And there was a time before when predators hunted in packs, mammals. And all of a sudden there were wolves and that type of canines that hunted in packs. And what that did is it changed the herbivory of herbivores, their behavior. Before then, they just kind of wandered around, kind of everything a little bit. All of a sudden, now there's like packs hunting them, and so they would be in herds. And they kick the old and the young and the sick out to the edge, and the strong ones kind of hang out in the middle or whatever. And they'd get picked off from the edges, but the ones that got picked off didn't have the herding instinct. And the ones that had the herding instinct propagated, and that's why they would feed in these giant bison herds. And what they would do is they'd come into a space 10 times the size of this room, a couple hundred of them, and they would just eat everything to the ground. And then they move on to the next place and eat everything to the ground. And the only thing that can survive that kind of intense herbivory is grass. Trees, you eat them off the top, they're not going to come back. They don't grow from down below. They grow out on their tips. Right? When you cut something, it doesn't grow back, right? Dicots, typically. Where grass, most of the plant is underground, and there's this little part of the plant that's like right at the surface, a little above and a little below, and it kind of sends up like an antenna. And so you can eat that down, and it just keeps sending it up. And so those grasslands created mollisols about 20 million years ago is kind of the number of when this happened. So mollisols are a relatively modern soil by soil terms or age. So this has been modified by roots, and then also there's secondary minerals that dissolve out of this and accumulate as iron oxides and clays. And that's where we're going next. We're going to go in deep, all right? If you get nothing else out of this talk, soil is habitat. By any measure, the most diverse habitat on the planet Earth. There's 1 billion organisms in a single pinch representing tens of thousands of species. And what do they eat? They live underground. They don't even know there's a sun. They're living in the darkness. You know what they're doing? They're waiting for stuff to die. And stuff dies. And when it dies, it falls to the earth. And what do? They don't get it to 451 degrees. No, they ooze out enzymes, which lowers the activation energy necessary for the oxidation chemical reaction to occur at ambient temperatures, and then they can get the carbon and the energy and respirate it out and the mineral nutrients, and that's why there's so many organisms underground, but they're secondary consumers like us. We can't sit out in the sun and get energy from the sun. We can't eat the atmosphere, so we eat the things that do, and that's why we're here. So, I mean, just look at this. So here is a little micrograph of a tiny little piece of soil. And it's like on the bottom there's a little scale. And this is about 1 millimeter by 1 millimeter, just for ease of description here. So if you were to like break off the lead of a number 2 pencil and look at that, that's what this is. So looking very closely. And what you can see is these are pieces of sand here. These bigger rocks out here. And then there's some silt, see the SI in between them right there? And then there's tiny little bits of clay in there. And look at these little bridges of water. Here's a bridge of water between 3 pieces of sand. This sand came from a river, this came from a volcano, and this one was from the bedrock underneath. They're all different kinds of rocks, and they're dissolving different nutrients into this ocean of water that's 1/10 of a millimeter in size, being held there by capillary force against the force of gravity. And in there is a giant sea serpent living in there. And that thing is trying to cower these things and eat them, but these things drink the poop of that thing, and this thing's over here waiting for all this shit to die, so that there's an entire ecosystem going on between 3 pieces of sand. And it's based on the type of rocks that are there and the frequency of water. Sometimes this little ocean of water shrinks back to almost nothing, and in the winter the whole thing's flooded. And all this stuff floods to a different location, and it's adapted to all of that change all the time, every year. And up here in the upper left-hand side, you can see, look, here's a root coming in, and this root is pumping out carbon sugars. And so plants ooze out carbohydrate in the form of sugar. About 10% of their photosynthetic production, they're just leaking out at their roots. And why are they doing that? To feed the microbes. Because the microbes need the energy from the sun that's in the sugar in order to make the enzymes to dissolve the organic matter from the dead stuff so that the nutrients will be released to the plant. And it's called a rhizosphere. It's a conceptual, like, stoner soil term. And it's this envelope that, like, were my hand a root, it would be like if I put on a glove that was 2 to 3 millimeters thick. That glove, that space that is the glove, is called the rhizosphere, is where the biologic diversity in soils is greatest, within 2 to 3 millimeters of a root. And that's because the plant is feeding the microorganisms there, because the plant doesn't have the enzymes to release the nutrients from the organic matter that's sitting around in the soil. And so the chemical signature of this body of water near the top is completely different. And has a different pH and a different salinity. And there's ciliated protozoa here. Look and see this spot right in the middle? That's a big pore right here in the middle. I don't know if you can see that. That was made by a root that went down in there, got bigger, died, and is gone. And now it's aerated, because that's a channel for air to move down to oxygenate this ocean so that those organisms can live there. And really, that is the secret sauce of soil management. Leave it alone. It's just, it will self-organize if you let it into a complex 4-dimensional habitat. Because that's why we're here. That's because that happened, right? That happened. And so minimizing disturbance is really the goal. Oh, not the goal, it's the action to get to the goal of a wide pore size distribution. So that it's a diverse habitat, so there's diverse organisms, so there's diverse functions to support plant life. Because the more plants there, the more carbon from the atmosphere, the more energy from the sun is pumped into the system, and it tends to become more self-organized. And that's why we're here. That's why we're alive. That's why there's macroorganisms on this planet. Because soil can do this other thing that we haven't talked about yet. Super important. The nutrients. Remember we talked about the nutrients coming out of the rocks, and they get picked up by the plants, and then we eat it and all that stuff. But what prevents the nutrients from just going down into the water table and going out to the ocean and becoming sharks? The ability of the soil to store those nutrients, not inside the rock, but on the surfaces of clay and organic matter. There are special properties that store the nutrients against the flow of water in a soluble form. They don't wash away because soil is sticky. It holds on to nutrients because soil is a negatively charged thing. Write that down. Soil is a negatively charged thing. And I'm going to show you why and where that comes from. We're going in deep. Soil is a living thing. It's not a chemical sponge. I mean, if you get nothing else out of this talk, if you can just remember this image and this concept that it's a living thing and it's a habitat. And your goal is to nudge it towards a wider pore size distribution so that it can do what it does. Instead of tilling the shit out of it, or compacting the shit out of it, or doing ever the shit out of it we shit on it for, all that shit. And you know, that shit's important, but you gotta know there's limits to it. Do you have to till the shit out of it? Maybe you could just half-ass till it. Because you're actually putting a tree in there. You don't need it to be turned into dust. But if you're putting in carrot seed, yeah, it needs to be very fine. You know, you need to grind it up nice so there's a seed-to-soil contact. So there's reasons to do it. But as long as you understand that the goal is to have a wide pore size distribution and let it self-organize. And then do what you have to do the job, but know when you don't have to do it. All right. So, reviewing. Soil is rotted rock, dissolves in water, and it's decomposed organic matter, and the rest of it is space, right? And so you look at the slide like this, and this is a pie chart that shows what soil is. And soil is, about half of it is stuff, and the other half is void, space. And what you're really doing as land managers is you're managing space, man. It's the space. Remember we talked about where the activity in soil is where it isn't, man. That's where the air is, that's where the water is, where the roots are, where the bugs are, there's the roots, and all that stuff happens in the space. And the space, depending on the size of the pore, is either filled with water or filled with air. And when do plants need air? And when do plants need water at the roots? All the time. So you need a wide pore size distribution, which they make themselves if you just let them, right? And you'll notice that minerals make up about 45% of the space, and that's sand, silt, and clay, which are different sized particles. And then there's this little slice called organic matter, where 5% organic, you gotta get a soil test if you really wanna know what the hell is going on. And 5% organic matter doesn't sound like a lot, but it's good. And I'm not talking about leaves and sticks. I'm talking about the black stuff that's coating all of the particles and welding them together to make macro aggregates that make for larger pores in between the macro aggregates and all that stuff, structure. And it's the kind of organic matter that hangs around for literally thousands of years in soil because it's encrusted by clay into an anaerobic environment that is unique. And inside that anaerobic environment are anaerobes that can fix nitrogen or from the atmosphere and feed it to plants and stuff like that. I mean, things you can't even, things we don't even know are happening. It's such an incredibly diverse habitat. So, here's a rock, same rock that I have in my pocket. And if we zoom in on it, right, those are the mineral crystals. And the minerals, some of them dissolve fast and some of them dissolve slow. And the white ones end up being sand and the rest of them become nutrients and are taken up by plants and animals and recycled in the living biomass and the organic matter cycle. But the ultimate nutrient cycling is the rock cycle. And that is mountains weather away and end up, and there's subduction when oceanic plates slide underneath of continental plates and they all get pulled down and the friction causes volcanism, which blows up volcanoes on the coast. And there's your real nutrient cycle on, 100 million year periodicity. And as long as there's uplift and volcanism and all that stuff and continental drift, there is going to be nutrient cycling on that scale. Place like Mars is cold out. There is none. And if it just rained on Mars all the time, it'd all be flat eventually. And all the molybdenum would be over here, and all the calcium would be over there, and then the bottom of this thing would be all where the lead is and stuff. And the nutrients would be dispersed all over the planet, so there couldn't be macroorganisms. But because of this system, it's constantly being turned around and churned up so that the nutrients are constantly being kind of spread out all over the place evenly, more or less, depending on the kinds of rocks, okay? So that's what's happening. So here, we were the size of normal life on the planet, which is in the soil, tiny little microorganisms. We're, very strange, we live at a very strange scale. And we live at this kind of, we think it's a long life, but really it's short. I mean, we look at a mountain. We could live here our whole lives and look at a mountain. And it's like, oh, that's not going away. But in 70, 80 years, no, it's not. But in 70,000 years, there's going to be a difference. In 1,000,000 years, in 100 million years, the whole thing is just dissolving away all the time. Even though it doesn't rain very much here, it does rain here. I mean, the pyramids at Giza, they're going to dissolve away. It's only been 4,000 years. That's not very long. 100,000 years from now, they're going to be gone. So don't worry about being remembered. Just give up on that. Just be here, okay? Don't worry about whoever in the future. I hate the people in the future. I love you. They hate us. And they're not even around yet. So anyway, but I love my students who are the future, but I love them because I love them now. Anyway, I don't know if I'm going with that. Anyway, just going with it. So would this be the size of a piece of sand? The relative size of a piece of silt is that, and the relative size of a piece of clay is actually 50 times smaller than the smallest pixel I can make on this screen. Relative to these sizes. So an enormous size difference between sand, silt, and clay. That means there's an enormous size difference between sand, silt, and clay size pores, and that's what texture is. And clay, this is where we're going. Sand is just a rock that ground down to the size of a piece of sand. 2 millimeters down to 2 millimeters down to 0.05 millimeters. Silt is just a rock that's been ground down. It's a primary mineral made in the hearth of the earth, somehow got to the surface and is weathering away, and it gets ground down or dissolves down or falls out as a crystal in the size of a piece of silt, which is 0.05 millimeters down to 0.002 millimeters. It's a range. And clay is anything that's smaller than 0.002 millimeters. Tiny little particle, clay-sized particle. Mostly, all these are made out of minerals, but increasingly there's plastics in sand, silt, and clay size in the soil, all that stuff. So it's just a size class. But clay is a different thing. Clay is not just a smaller rock. Clay forms when rocks dissolve, and then the components that are dissolving out of the rock recrystallize at normal surface temperatures and normal surface pressures like we feel here. Not in the hearth of the earth, high pressure, high temperature, but at like ambient temperatures and ambient pressures. So when rocks dissolve, there are certain parts of the rock, in fact, the four most abundant elements in the Earth's crust are iron, aluminum, silicon, and oxygen. Rocks are mostly made out of oxygen. What? Too bad. Where do you think the oxygen came from? I mean, so when those four elements are dissolved out in certain ratios, they recrystallize at the surface of the earth. And the crystals, you can all think of a crystal growing. You've all done this. You've all had this kind of stoner moment where you're watching a crystal grow at the edges and get bigger like a plane, and it's growing and it's growing. And this crystal can only get to 0.002 millimeters before it breaks. It doesn't have the stability to get any bigger than 0.002 millimeters because it just doesn't have the structural integrity to get any bigger. But then it grows again, and then it breaks. And it grows, breaks. And as long as there's dissolution products dissolving out of the primary mineral that supply this crystal to grow from its edges, it will do that. And that's what clay is. Clay is formed at normal surface temperatures and normal surface pressures. It is the product of dissolution and recrystallization. When primary minerals dissolve at the surface of the earth, many of them become nutrients, but some of them form crystals that can get to 0.002 millimeters, and that's what clay is. It's a different thing. And clay-sized particles have clay-sized pores between them, which hold a lot of water. And that's why clayey soils hold a lot of water. And sandy soils don't, because they don't have large particles, large pores that drain into the force of gravity. That's why a loam is about right. Equal parts sand, silt, clay, more or less. All right? So, rocks dissolve in water, And look what dissolves out of them. Nutrients. Potassium, phosphorus, calcium, yeah, all of it, right? Dissolves out of rocks, including silica, iron, aluminum, and oxygen dissolve out of there, four most abundant elements in the Earth's crust. And when those four most abundant elements in the Earth's crust encounter each other under the right conditions, they recrystallize into something called clay, which are sheets, thin sheets of silica and aluminum oxides, kind of like rust, but not iron. That's all, just kind of like that. It's a thing that sticks around, actually. Clay is actually fairly stable at the surface of the Earth, where rocks are kind of unstable, because rocks are formed under different conditions where they're less stable at the surface of the Earth, where these are formed at the surface of the Earth, so they're more stable. Otherwise, they wouldn't be there. Okay, you got that? We're going in. You ready for this? Okay, so, yeah. So here, these are the building blocks, the tinker toy parts that you can put together this crystal with. When a rock dissolves in water, the four most abundant elements in the Earth's crust, iron, aluminum, oxygen, silicon, that's what's dissolving out a lot of. And as it turns out, silicon is an element that has a certain size and a certain charge on that forms covalent bonds with oxygen. And it forms a silica tetrahedron. Okay? You wanted to learn something today. Okay. Pay attention. Because this is the reason you're alive. This is the reason there are trees. Okay? Just saying. If it wasn't for the ability for the soil to store nutrients, all the nutrients would be out there, mostly be sharks. And maybe some little pond scums that could handle the little bit of nutrients that are around. But soil stores nutrients because of, pay attention. Silica tetrahedron is silica has a covalent bond with 4 oxygens and forms a silica tetrahedron. And over here is aluminum octahedron. It's like 2 4-sided pyramids stuck together. This is 1 3-sided pyramid, right? And aluminum has a certain size and a certain charge that forms bonds with oxygen, with 6 oxygens, and forms the aluminum octahedron. These oxygens, in this case it says hydroxyl groups, but still, these oxygens can be shared, and that's the crystal growing. The silica tetrahedron comes down, and it locks on. Next one comes down, and then aluminum octahedron, and it comes on, and they keep growing, and they build this thin sheet that can only get to 0.002 millimeters before it breaks. And then it grows when it rains. And when it's dry, it shrinks up, and it kind of waits until the next season. Then it grows, and then it shrinks, and it breaks, and on and on and on and on. And that's what clay is. So, get the silica tetrahedrons and the aluminum octahedrons. As it turns out, there are other elements weathering out, dissolving out of the rocks. And some rocks have a lot more magnesium in them. And some rocks have a lot more iron in them, right? Because they're dark colored or whatever. Rocks are not evenly distributed on the planet. That's why there's not an even distribution of soils on the planet, which is why there's not an even distribution of political power on the planet. Just saying, it's all about geology and climate that begets this moment. You know, this is reality, man, right now. This is it. This is the only life we have, is this moment. And the fact that rocks dissolve in water and the sun is giving UV radiation to this planet, plants figured out a way to eat the atmosphere and do that, all that, that's it. That's reality. And everything else, complete fantasy land. The rest of it is just derivative of the facts, the basic facts of how the planet actually exists. And just, you know, keep the perspective, all right? What matters? Soil. Nothing else matters. It's all about soil. I think that was the first line of this talk, wasn't it? I think so. But check it out. So in a weathering environment where there's lots more iron, instead there might be, oh, sorry, what happened to it? Oh, dang. Yeah, get to that. Hold on. I changed the slide. super important. I hope I didn't get rid of that. Did I? Ah, here it is. Oh, that was right. Okay. Sorry. No, don't do that. Jesus. Stop, Cassidy. Stop. Okay. So look here. Can you see? Look at, here's the silica tetrahedrons making a sheet, right? And then there's the aluminum octahedrons making a sheet, and then there's the silica tetrahedrons. You see that? And this is the growing edge of the crystal. And it keeps growing, breaks, breaks, right? And so this whole thing is called a 2-to-1 clay, because there's twice as many tetrahedral sheets as there are octahedral sheets. And you'll notice that this whole thing is called a layer. And there's another, and another, and another, and another, and they stack up by the millions until they get to 0.002 millimeters. And then they fall over. Like if you were to stack books, how high could you stack? Think of all the layers in a book. And you can stack them so high before, whoa, they fall over, right? And so that's kind of what's happening. So this is surface area. Inside, in between the pages of the book, water can flow in and out. Nutrients can flow in and out. That doesn't happen in a rock, okay? So can I borrow this just for a second? This is what clay is like. It's sheets with giant surface area. In fact, thank you so much. Here's a card. It says soil on it. You got one too. So, and this is going to kind of blow your mind. If you were to take a thimble full, anyone know what a thimble is anymore? You will pretty soon, because you're going to be sewing your own clothes. Okay, so you ready for that? So you take a thimble full of sand, and if you were to measure all the surfaces on that sand that's in there and spread it all out into a sheet, it's about the surface area of a sheet of paper on both sides, okay? If you take a thimble full of silt and measure all the surfaces in there, it's about a big paper newspaper or something, maybe like a yard of paper on both sides. You take a thimbleful of clay, has a surface area of a football field, okay? Because of the pages, the layers. And it's only 0.002 millimeters, but there's a lot of them in a thimble, and it's a lot of space. And where is the activity in soil? Where it isn't, in the space between the sheets. And it's like, man, yeah, see, we're at the wrong scale. We never know this. How would we ever know that? Unless there was somebody invented electron microscopy because they weren't growing the food, because somebody else specialized in growing the food so that they could be some research scientists and find out how things work so that we could grow food for all of us. Just saying. You know, there was a time before all of that. Before people grew their own food, they traveled with the animals and the seasons. And at well, I can't tell the whole story, but we became sedentary because we could grow surpluses. And once that happened, we live in the shadow of the invention, which was a technology, the invention of agriculture. We just live in the shadow of it. The agricultural revolution begat the industrial revolution, which begat the information revolution, which, you know, was the end of all things. So thanks a lot, ancient agriculturists. Things were going pretty good here for a few million years. So here's this. So now if we zoom in on this again, these building blocks, if there's certain other stuff like iron, which has almost the same size and almost the same charge as silicon, it can become substituted into the tetrahedral sheet at the time of recrystallization. Almost the same size and almost the same charge, right? Same thing happens when there's lots of magnesium in the rock, dark-colored rocks. So now you got, instead of aluminum octahedrons, you got magnesium octahedrons in there. And magnesium is almost the same size and almost the same charge as aluminum, but not quite. But it still fits into there. So now you've got these substitutions that are occurring for silica. And look, remember I said almost the same charge? Meaning there's a little bit of negative charge left over. Sand doesn't have a negative charge. Silt does not have a negative charge. Clays And the secondary mineral called clays, when there's isomorphic substitution into the crystalline latticework at the time of recrystallization of the secondary mineral called clay, can have a negative charge that's propagated to the surface. And you might recall that a thimbleful that has the surface area of a football field, and now you've got negative charges on that surface. Same thing happens in the octahedral sheet with magnesium, and now you got more negative charge. You know what sticks to negatively charged things? Positively charged things. You know what the charge on most mineral nutrients is? Positive. So now you've got this clay thing that's very small, and it's maybe not even very much of it. It doesn't need to be very much. 10-15% clay in your loam that has young clays in it, that have a lot of isomorphic substitution, that have a lot of charge on the surface area, can store mineral nutrients temporarily. It's an electrostatic charge. Like, you know how a balloon sticks to the wall? It's a static charge. It's not bonded. It's just kind of stuck there. And it's stuck there tight enough that when it rains, it doesn't wash away. So in the winter, when it rains, I don't know if it rains here, but in the summer it rains here, right? Well, it doesn't rain anymore. But back in the times when it used to rain here, if it wasn't for the negative charge on clay, the nutrients would just wash off in the oceans and become sharks. Instead, they're storing there enough in the surface layer that the plants can then get the nutrients when they need them because they're stored there. Okay? So you kind of get that? I mean, that's a lot. But it's the reason for the season, literally. I mean, this is why it happens. So isomorphic substitution is a source of negative charge on soil. So isomorphic means same size and shape substitution into the crystalline latticework. As the crystal is forming, this is happening. And the crystal itself dissolves and recrystallizes, too. So that's happening. So just saying. So look at, here's 100,000 times magnification of clay. Electron microscopy. Okay, somebody invented this shit so that you could just look at it and go, holy shit. That is reality. This, I don't know what this is, but there's a lot of love in this room, I know that. Whatever that is. Whatever that is. That's desperation is what it is. Anyway, we are alone. When you're laying in bed tonight, I want you to remember this image. Actually, you're never alone. There's, in the sockets of your eyelashes, there's nematodes. And imagine what's going on in your shoes right now. It's just like, you're fine. Under your nails, just like, what's on this table? Don't worry about it. There's nothing on this carpet that can kill you. I mean, shit. I mean, this is us. It's just the grease of humans everywhere, all over us, up in us, all around us. Gadzooks. So look at 100,000 times magnification. Look at the layers. You see them? It can only get to about 0.002 millimeters, and then it breaks and starts growing. So it can only stack up so much before it falls over. And there's net negative charge all over those surfaces due to isomorphic substitution, secondary called clay. Look at this clay, right? That's like 70% space. And there's net negative charge all over due to isomorphic substitution, secondary called clay. Look at this clay. Like 90% pore space. Looks like fiber. Different kinds of clays form from different kinds of rocks. And there's net negative charges all over that thing due to isomorphic substitution, the secondary called clay, at the time of recrystallization. Look at that. That's like a crystal of your fantasies, right? There it is. Like, oh yeah, that's how I get it. Net negative charges. Look at this one. Net negative charges. Look at this one. I mean, just look at that thing. Built up atom by atom from dissolved rocks. Imagine the tip of that, how sharp that is, right? And it's got net negative charges all over due to isomorphic substitution, a secondary called clay. So everyone together, are you ready? Let's just say this together. Here we go. 1, 2, 3. Net negative charge due to isomorphic substitution on the secondary mineral called clay is the reason you're alive. There's a reason there's trees. Because if it wasn't for that, there wouldn't be enough nutrients stored in the surface layers of the soil for a tree to ever be. Because there wouldn't be enough phosphorus to build the phospholipid bilayer. Or there wouldn't be enough nitrogen to make amino acids and proteins. Or the nucleotides to store the information to tell it when to close the stomata. Come on, man. You want a miracle? Hello? Here it is. You're living it right now. This moment is already gone. Think about it. In your mind right now, there's electrical impulses that originally came from energy that was harvested from the sun so that you could remember things in the past so that by the time I get to the end of the sentence, you still know what I'm talking about. That's all happening in your mind because of the laws of physics and the fact that rocks dissolve in water and plants have figured out a way to eat the atmosphere using the energy of the sun. And everything is derivative of that. Man, free your mind, man. You're free. I'm not trying to make soil scientists out of you. I'm trying to make soil citizens out of you. My goal today was to change the way you see reality. I didn't tell you that at first. Usually I lead that. All right, look at that. There's clay. Look, calcium. See, it's stored there, just kind of hanging out there. Every calcium ion in your skeleton was once on the exchange complex of clay, dissolved out of a rock. Look at this one. Look at calcium, magnesium, potassium. That's what fertilizing is. When you add fertilizer to the soil, whether it's in a form of organic matter like kelp meal or something that has a lot of potassium in it, and then it gets broken down and released as potassium, or you put on some chemicals or whatever. What you're doing is you're loading up the negative exchange sites with the nutrients that you want in the proportions that you want so that when the plant needs it during the growing season, it'll be there. And it may not be enough of it from the native materials to grow that. I mean, you know how people are. They live in Arizona or wherever they live where it's dry, Flagstaff, say, and they want to have an English garden. It's like, how about just no? You know? It's like you can't do it. You can, but you got to pay for it. So look, right? Soil is rotted rock and decomposed organic matter. So we talked about clay. And that clay has isomorphic substitution on it. And that causes a charge that can store nutrients, right? Turns out there's one other thing in soil. Guess what it is? Turns out there's one other thing in soil. Isn't that? Yeah? Turns out there's one other thing in soil called organic matter. And organic matter, I'll get through all that. Here it is. Organic matter is a random molecule of leftover dead stuff. I mean, this little piece right here was like in a monkey's paw. And this, you know, came out of like some plant seed coat or, you know, whatever. All this is a random molecule of leftover dead stuff. And as it turns out, organic matter itself has the same kind of surface area as clay. And organic matter itself has a net negative charges all over it too. Not because of isomorphic substitution, but because it's a random molecule. And because it's a random molecule, when light shines on it, because it's random, it doesn't reflect back any particular spectrum in the electromagnetic field, so that it looks black. And it absorbs energy, and dark soils get warmer faster. So organic matter not only warms the soil, is carbon and energy, it also has negative exchange, it has charge on it. And it's food for organisms, and it's nutrients for the next generation of plants. What's the answer? Add organic matter, because when you're adding organic matter, you're actually increasing the negative charge. You know what that negative charge is called in your soil test? It's called the cation exchange capacity. Some of you may have heard of that. It's a number. You get a soil test, and it says, what's the cation exchange capacity in my soil? And what that number is the number of negative charges on the soil, whether it's from clay or organic matter. And there are two different tests to get that number. And the total number of charges, what the number is, and it's a number that goes from 5 to 40 in most soils. And you're like going, and if you have 20 or more, you can grow anything. If you have a CEC of 20 or more, you can grow food crops. If you have a CEC of 10 or less, it's probably sandy soil. And because it's sandy soil, it doesn't have a lot of clay. That's because it's dry, right? Because it drains. And so there's not a lot of water to create clay. And because there's not a lot of clay, there's not a lot of nutrient storage. Because there's not a lot of nutrient storage, there's not a lot of organic matter. So there's not very much organic matter. So the CEC is low. And the cation exchange capacity, that number is per kilogram of dry soil. A clump of dry soil will be about as big as a softball. And so 20 means it's 20 times 6 trillion negative charges per kilogram of dry soil. They just lop off the trillion because they don't want you to have to know that. But it's 20, a CEC of 20 is 20 times 6 trillion negative charges per kilogram, which is twice as much as 10. You know that. So 20 can store twice as much nutrients for plants. So how do you increase the CEC of a soil? Add organic matter. You're not going to add clay. First of all, where are you going to get the clay? From whose dead, cold hands are you going to take clay from? And it's just easier, never mind. It's easier just to go take the land. But it is ugly little world. But you can grow organic matter, and that's what cover crops are. You grow and you mow and you blow, and you do all that stuff to add organic matter. You get compost, you put it on the surface. The bugs will take it in. You don't have to work it in. That's what you want to do, because what you're adding is carbon and energy and cation exchange capacity and water holding capacity. Organic matter itself, pure organic matter, can store 80 times its own weight in water. In fact, recently I saw on the NRCS website, if it's still up, that by increasing the organic matter percent in your soil by 1%, which is not easy to do. It's not just pouring a bunch of crap on it. It has to biodegrade. It's the stuff that's really left over, the black stuff. If you can increase the cation exchange, increase the percent organic matter of your soil by 1%, you can store 25,000 gallons more water per acre. And that's the difference between breaking the budget or not if you're paying for irrigation water, right? So increasing organic matter not only increases the cation exchange capacity, not only does it allow the soils to warm up a little faster, not only does it help with aggregation, not only is it carbon and energy for organisms and the next generation of plants, it also stores 80 times its own weight in water. That's why it's the answer. And that's the foundation of what soil building is. It's this idea that organic matter is accumulating because plants figured out a way how to do it. Right? So, here's a plant. Let's look at it up close. Above ground and below ground. Amazing critter. Has two habitats. Look at the above ground. There's these flat green things, these things, and whatever there are, and the above ground stuff, whatever. And what they do is they're flat, and they actually evaporate at their leaves, which drops the pressure of the water inside of the plant, which allows for a suction force to pull water in at the roots. And where is the water? In the small pores, right? And then they eat the atmosphere, and that process of eating the atmosphere and using water, etc., produces oxygen, which is given off. And then the mineral nutrients are stored there and are being taken up at the roots. And then most people, other people, not you guys, but most people don't have no concept of the idea that plants breathe oxygen at their roots. They breathe for the same reason we do, to have a final electron acceptor to dump electrons onto so they can create ATP and blah, blah, all that stuff, right? So they can do cellular work. They need that. And if you've ever, who here has ever drowned a plant? Come on. If you're not raising your hand, you're lying, okay? My ex-wife once said, if you're not killing plants, you're not growing as a gardener. So I've killed a lot of plants in 25 years, and I've learned a lot. So okay, so here's what happened. So we're zooming in. Look, this is some of the last slides, so pay attention here. On the left, there's the plant. And we zoom in on that little circle there into the big circle here, and we see here's the root, and there's the little tiny root hairs, the tiniest root hairs you never saw because they're silt-sized or clay-sized little threads. And where are they going? Into the small pores. And what's in the small pores? Water, right? We zoom in on the one plant hair, just that little root hair. We zoom in on that, and what do we see? Look, above it, there's a soil particle. And look, it has a negative charge on the surface. And how did the negative charge get there? Because of isomorphic substitution of secondary mineral clay and organic matter coatings. So a piece of sand can be coated with organic matter and then have negative charge on it. So all sandy soils don't have to have a low CEC if there's organic matter present. How do you get a sandy soil to have more higher CEC? Add organic matter. Right? So now look, here's the root hair. And look what you're seeing. Look at the nutrients. They're stored there temporarily, electrostatically, on the surface of the clay particle. And look what's stuck there. Calcium, potassium, magnesium, potassium, right? All the nutrients that you put on there as fertilizer or just in nature, they're there. They're stored there. And what plant roots, what they do at the root hairs is they exhale CO2 there. And when the CO2, and this happens in the growing season more, and that CO2, because of respiration, that CO2 dissolves in water. And you all know that CO2 dissolves in water. Because if you've ever opened a can of soda water and the bubbles come out, that's CO2 that was dissolved in the water. And when CO2 dissolves in water, it forms carbonic acid. That's this chemistry you see here, a little bit of chemistry. That's carbonic acid, and that's what makes it taste sort of lemony fresh. It kind of has bite, right? Good root beer has bite because it has carbonic acid in it because we dissolve CO2 in it, which changes the pH and makes it more acidic. And the carbonic acid further dissociates into hydrogen ion and carbonate ion. Don't worry about it too much, but the main thing is this process produces hydrogen ion, which is what acidity is. You measure acidity by how many hydrogen ions there are. So the plant is acidifying the water in close proximity to the soil particle, which has the nutrients stored on it. Pay attention now. This is it. We had to do all of that to get to this, okay? And this is like critical stuff. And the more charges there are, the more nutrients can be stored, right? And we can affect that by adding organic matter or going somewhere else where there's clay. And what happens is, this is something we haven't talked about yet, these nutrients, they have different sizes and different charges on them. And as it turns out, some of the nutrients are more strongly absorbed to the exchange complex than others. Some are kind of hanging there electrostatically, kind of, oh, it's all right. And some are really tight. And in fact, the smaller the ion is, because of Coulomb's law, the closer the ion can get to the negative charge, and the tighter it gets. It's like taking two magnets, not magnetism, but it's like taking two magnets, and when they put them together, it gets harder and harder to put them together. You flip it around, harder and harder to keep them apart. Because over that distance, the closer that charge can get, the positive charge can get to the negative charge, the tighter it's held. And some of these ions are giant in the normal size of things. Like sodium ions are huge, and they're just kind of stuck there. Whoa. Where, as it turns out, the most strongly absorbed ion of them all is hydrogen ion, which is being produced by the plant because it's exhaling CO2 into the water, forming carbonic acid dissociating to hydrogen ion. So now there's a lot more hydrogen ion present, and you know what? The hydrogen ion says, hey, calcium, you're kind of weakly stuck here. You're off. And it kicks the calcium off. And the hydrogen ion sticks there. And now what happens to the calcium ion? So, whoa, where am I going? Oh, I'm moving towards this root because there's evaporation at a leaf and gets pulled up into the plant. and it goes up into the plant and becomes part of the tissues. And then it becomes part of the plant, and it does whatever it has to do. And then you eat it. And then you biodegrade it in your gut because you have a, look, there's a hole here and a hole here and a tube going through, you're right. And the soil is in there. You're living around a tube of soil. And you're going, please, please. And it says, feed me or I'm going to eat you. So, okay, well, let's keep feeding it, whatever. It's we're like an inside-out carrot. Where a carrot is a tube that lives in the soil and gathers nutrients from around it. We flipped it inside out. And we were living around the tube of soil, and we're feeding it organic matter. And so now that's how every nutrient in your body got there. Every nutrient ion in your body was once stuck to the negative exchange complex of clay and or organic matter, and it was stuck there. And then a plant had a root, and the root hair that acidified the water during the growing season because it's pumping out CO2 for carbonic acid and releases more hydrogen ion, which exchanges the nutrient off of the exchange complex, and it flows into that's how plants get the nutrients. So we've kind of come full circle on this, you see what I mean? So, if you look real close, like an image like this, well, this one, you could see maybe there's like a little halos kind of like of root hairs, tiny little root hairs. The tiny little root hairs, they almost look like fungus. And fungi are doing the kind of, everything's doing this. The fungi are doing the same thing too. They're pumping out CO2 and releasing nutrients, and that's how they grow. And the bacteria are part of this process too. They're all going for the same nutrients. See that little halo of little roots? And look at, there's a large pore being made by the big part of the root at the top. And then there's medium-sized pores being made, and then there's tiny little pores going into the tiny little aggregates that have the water stored in them. And that's how it works. Now check it out. So here's all the macro and micronutrients underground here being taken up by plants. And those plants, those things do things in the plant, like seed quality and storing nutrients or photosynthesis or whatever these nutrients are doing. And then we eat them, and they do things in us. Many of the same functions, in fact. I mean, every blood cell in your body has something called hemoglobin in it. Most of you know that. And hemoglobin, heme is iron. There's a little piece of iron in the center of that. And it's a gas exchange molecule, and it has these unique properties. But where did that iron come from? It dissolved out of a rock and was taken up by a plant because it was stored on the negative exchange complex of clay and organic matter, and then you ate it. And that's why you have hemoglobin in you when you're alive. So, amazing. So, oh yeah, I do have these shirts for sale. But we can get to that in a minute. But won't you please, look at I have them in curvilicious and straight styles. However you want to, however we do this now. And go to soilforward.org. And I have them in Klingon and Vulcan. So something for everyone, right? You know who the Vulcans are. You know who your Klingons are. They all need soil, though. It's the ultimate leveling topic because it's a fact, and it's where everything comes from. It's where everything goes. And if you want to, you can just get this QR code if you want to. And I'm going to go on some other stuff here in just a second, but I just want to get this out of the way. That 100% of these T-shirt sales go to fund my student intern program. And I have like 13 of them. They're $3,000 a summer. And we pay for it. We're self-funded through the sale of fruit and vegetables. And they used to try and throw us off the land because we squatted on it. And they said, hey man, you're squatting on it, bro. And they didn't like that. And we just kept coming back. The administrator said, well, those kids do not, they're probably just growing weeds out there. They're probably even growing weed and get high out there, blah, blah, blah. It's like, yeah, okay, whatever. You mean kids are having a good time learning them by themselves? I know that's kind of a threat, probably, to the institution, that they want to have fun and learn together for free on stolen land. Anyway, so preparing them for the American experience. And you know what? Those people who tried to get rid of us 25 years ago, they're either retired or dead. So they ended up adding to our project in their own way. And, you know, we didn't necessarily bury them there, but sooner or later, somebody's going to eat them. And I just have to show you one more thing. Are we done? Yeah? I'm going to show you one thing. So there's an app for your phone. I know a guy comes, talks to you, and then he brings out his phone. And it's called the Soil Web app. Some of you probably already have it. Hey, who here has taken my class already? One right there, front row. Look at that. Okay, very good. Were you at the student farm ever? What year was that? 2009. Wow. Yeah, man. I remember you. You didn't sit in the front row, man. No. There's an app called the Soil Web app, and you can get it for free, and you upload it right now, and you get a gold star. First person who gets it. And you can just hit Get My Soils Data, and it will geolocate and tell you what soils were mapped here. Now, they built this building. They probably ripped it all out and put it in concrete, whatever. But what the soil is mapped of, anybody have it yet? No? No yet? Okay. And underneath this building is something called Blue Point. It's one of the 20,000 different soils, and it's a typic Tora salmon. It's an entisol. Sam means sand. Tori means hot. So it's a hot, sandy entisol, and it's typical. And there's an app that I put in here from the California Soil Research Lab, and it can take us right to where we are. And we can see what the soil types are anywhere, and you can just like, as soon as there they are, you click on that. And right there's these soil types. And man, we didn't even scratch, we just barely getting started here, but we had to do those basics. But you can see, look how thin that soil is on the left. Bedrock at 46 centimeters. That's it. That's the soil, like the iridisol. And is it an iridisol? No, it's an entisol. An entisol is the entry level. It means it's really sandy or young. Where an iridisol can be old and well developed. An entisol is a very young, probably because there was a river went through here, right? At one time. And it's a lithic, meaning that's the rock, has lithic. So it's a lithic tori orthent. Tori means hot, and it's an entisol. This node is rock under here. The reason there's all these here is because the probabilities of any one of these exists in this area, or where I geolocated. And here's an iridisol. See the K, the BKs? I don't know if you can see that on the iridisol. That's salt. Remember the salt layer we looked at on that first couple of slides? Yeah, you got it? All right, look at this. A+. All right. I don't have a gold one, is that all right? I got a blue one. I think that one gets you a whiskey.
Oh, there you go.
And there you go. Bumper sticker for you. Oh, yeah? Is that where we're at now? Okay. So, okay. And there's a typic calci, look at, a typic calci argid. It's an iridisol that has a clay layer. See T, BT, that means clay. Why is there clay below ground a little bit? Because water washes down, dissolves out, and it reprecipitates at a lower level. So usually you get clayier soils a little below the A horizon. We didn't even talk about soil science, really. We were just too busy talking about soil. But all this was mapped by the previous generation. After the creation of the Soil Conservation Service, they sent out hundreds, thousands of people to go out and map the soils of the country. And I was the president of the Oregon Society of Soil Scientists 3 times. And I was kind of like the beginning of the end because those were mostly soil mappers who came to that meeting, and it was really cool. And go to the Oregon Society of Soil Scientists. I'm getting the hook here from dear old dad here saying enough. I just want to see what's going on over here. Oh, yeah, rocks. Over here. Okay, so that's all I got for you today. And try the shirt. Do it for the kids. Do it for the kids. The next generation is the future. Is that hard to understand? I don't know why, but they literally are the future. Support the kids. Buy a t-shirt. Thank you so much.
Now we know where it comes from. There's a half-eaten piece of brownie.
I want that. That's mine.
No, that's yours.
Yes,
I know. It keeps it going.
God, I couldn't get to it.
Yeah.
You know what the answer is?
exuberance,
Yeah.
passion, authority,
I don't know about that.
and the humor, blend those together, and this gentleman is a master
Oh, man.
at technology transfer.
Yeah. Well, question authority, I would say. So.
And on behalf of
Oh my God, here it is.
on behalf of everyone in the audience and
Wow.
Think Trees,
Wow.
Think Trees Conference 2025, James Cassidy, in appreciation of your participation and support. Thank you, sir.
Thank you
so much.
Really
Thank
appreciate
you.
it. So nice to
Okay,
meet you,
good.
man.
Thank you.
Yeah, look at that. You get this hot enough, and it'll burn. So,
Thank you.
all right.